Welcome back. Okay. In this class, let us start looking at unsteady state heat conduction. We've already seen an example of steady state heat conduction. So, the next aspect is unsteady state heat conduction. What does unsteady mean? We all know, right? That the temperature, the variation with time at a point in the system does not happen. Variation of relevant properties at a point does not happen. The, the values remain the same with time. Again, let us pose a problem, solve it. Okay, all these will serve as problem solution strategies also, and we pick up the relevant principles, relevant tools as we go along, okay, in the context of the problem itself. This problem reads as, in a microanalysis system, for the determination of an analyte, the sample is first sprayed as 10 microliter. That has to be microliter. Let me correct it right away for you. Okay, in a microanalysis system, for the determination of an analyte, the sample is first sprayed as 10 microliter spherical droplets into a heating zone. The droplet needs to be heated to 60 degrees C to complete a reaction that is a necessary step for the analysis. Okay, this is what we have here in a very standard situation, especially in microanalysis. Assuming that the properties of the sample drop are the same as that of water, since the sample is predominantly aqueous, so that's not a bad assumption at all. Estimate the time needed to reach the steady state temperature in the droplet. Okay. The droplet needs to reach a temperature of 60 degrees C steady state for the reactions to have been completed at this step, and we are asked to find the time that it takes to reach. Okay, very relevant, because our heating rates must be adjusted such that there is not much time needed for the entire droplet to reach steady state. Okay, that's the whole idea here. So this is probably a question that is raised at the design stage as to how much of heating should be there so that the time is minimized, or if we have this much heating, is it good enough? How long does it take? Maybe there is a heater that's already available, the company wants to use it, the designer wants to use it, and wants to check whether that will serve the purpose. Very many different situations. Okay, for all those situations, this analysis becomes helpful. Okay, that's the beauty of this. Fundamental application is just up to us. Rather, whichever, it can be used in very many different ways. Let's go about solving this. We are, of course, dealing with a sphere, so obviously spherical coordinates are the ones that are relevant. We are going to use the equation of thermal energy here, so just go to that table, pick up the relevant equation. So in this case, the spherical coordinate equation. And of course, for a laminar, a Newtonian fluid, in this, yes, water, Newtonian fluid is perfectly fine, or predominantly water, Newtonian fluid is perfectly fine. Constant rho and k can be assumed in this case, so that's not a problem. So equation C2 we could pick up from table 4.2-1, and if we cancel the irrelevant terms, what I'm going to ask you to do is stop or pause the video here, go back to that equation, or pick up this equation C2 from 4.2-1, cancel the irrelevant terms, see what you get. Okay. Then we will continue. Okay. I think you need to pick this up. So why don't you do this, and then when you come back, we'll see whether you got the same thing. Go ahead, please. Take as much time as you want. Time is not a big, time is not a big constraint here. Go ahead, please. I hope you got this as the remaining terms. Dou T, this is at unsteady state. The temperature inside the droplet continuously varies. The temperature inside the system continuously varies. Therefore, this term is highly relevant. Okay. equals k by rho Cv 1 by r squared dou r squared dou t dou r. So these would be the only terms that remain. And as you know, we have a time derivative here, a partial differential equation, along with, of course, the space derivatives. Okay. So the mathematical effort that is needed is going to be quite significant to solve this. Let us solve this. I'm not going to show you all the steps. You need to, now you have enough. I've shown you individual steps, each and every individual step so far. So now I'm going to let you figure it out yourself. That's the only way you'll learn. So let me show you the solution. It's not highly trivial. So I'll show you the solution, but I want you to fill in the intervening steps. Okay, please do that. That's the only way to learn. So this is equation 4.2.2-1. Let's define the non-dimensional variables. K by rho Cv is alpha, okay, thermal diffusivity. Let us say that the drop surface temperature being raised to 60 degrees C Ts at the start of the cycle. So the surface is already at 60 degrees C when you put in. It is how the temperature varies inside the drop that's our concern here. So at time t equals 0, the initial condition, the surface temperature is at 60 degrees C. Therefore, the initial condition for r equals, for 0 is, or r between 0 and r, at time t equals less than or equal to 0, t equals T0. Okay, so the entire droplet is at T0, okay, some T0, and the surface temperature is Ts. That will come to in a little bit. This is the initial condition, T less than or equal to 0. Now we need two boundary conditions because it's a second order variation in space. Before that, this is equation 4.2.2-2, the initial condition. The boundary condition at r equals 0 at the center, again spherical symmetry, and of course t greater than or equal to 0, dou r t equals 0. Whichever direction you approach, you need to approach the same temperature at the center, and that is possible only if the temperature is either a maximum or a minimum at the center, which means the derivative of temperature with respect to the radius will be 0, extremum condition. This is equation 4.2.2-3. Boundary condition 2 is quite straightforward. At r equals r, the surface of the droplet, and time t greater than or equal to 0, t equals Ts. So we have the initial conditions, we have the boundary conditions, we can solve this. Of course, we'd like to solve it in terms of non-dimensional variables, makes the solution a lot more general. So let us define the following non-dimensional variables. Eta as r by r, the distance variable, a theta temperature variable as T minus T0, the entire initial, the temperature at which the entire droplet is initially, divided by Ts, the surface temperature, 60 degrees C minus T0. Okay, that's what we are going to define our theta as. And then we are also going to define a tau, okay, because there is variation with time. None of these show a variation with time. Tau as alpha t by r squared. Okay. Work out the dimensions. This is quite straightforward to see. This is quite straightforward to see. Work out the dimensions of these to ensure that tau is indeed dimensionless. So in terms of the non-dimensional variables, the differential equation and the initial boundary conditions will become, do work this out, it is quite a few steps, do work it out and check for yourself. Dou theta dou tau equals 1 by eta squared dou eta, eta squared dou theta by dou eta. Okay. That's what the initial equation will turn out to be in terms of the non-dimensional variables, differential equation, partial differential equation. Equation 4.2.2-5, and the initial condition for 0 is less than eta is less than 1 inside the pellet, at tau less than or equal to 0, theta equals 0. The boundary conditions being at eta equals 0, t is greater than or equal to 0, dou r of theta equals 0, the symmetry condition, and the other one being at eta equals 1 at the surface, tau greater than 0, theta equals 1. Okay. So we have the partial differential equation in terms of the non-dimensional variables. We non-dimensionalized it, and we have the initial and boundary conditions in terms of the non-dimensional variables. We can solve this, and for solution you'll have to go back to your math course, right, your differential equations course, see how to go about solving this form. Okay. Of course, here we cannot apply separation of variables. Okay. Check out why. Boundary conditions need to be homogeneous. Try to understand that better. And then if you follow a method that will be suitable here, that is going to be something like this. Let us use the following transformation. We are going to call a theta dash, which is a function of eta and tau, as 1 minus theta. Okay. So if you do this, equation 4.2.2-9, then the transform problem, which is the differential equation in terms of this, is going to be dou theta dou tau equals 1 by eta squared dou eta squared dou theta by dou tau, dou theta dou tau. Okay. Work this out and check. Equation 4.2.2-10. For 0 less than eta less than 1, tau, we need the boundary conditions also in terms of the transformed variable. Therefore, this is going to be the initial condition, theta dash equals 1, and for eta equals 0, the dou theta dash dou r is going to be 0, the symmetry boundary condition, and for eta equal to 1, tau greater than 0, theta dash is going to be equal to 0. Equation 4.2.2-13. Now, if we define f as theta dash eta, then equation this becomes dou f dou tau equals dou squared f by dou eta squared. Try that out and see. We are going to define f as theta dash times eta, and then this equation will get into this form. You will have to first write it, then differentiate it, and see that it indeed reduces to this form. Okay. So this is, we are getting closer to the way things are given in the textbook, because I have spent enough time to prep you to see how condensed things are in the textbook and in other textbooks. My textbook has a lot of details given, maybe not here, maybe initially, and here the idea is to get you into that framework, because the information is available only in this form. You need to fill in all the gaps. Many people don't realize that you need to fill in so much gap that they are usually confused, okay, or wonder how can you go from this step to this step. This is equation 4.2.2-14. The solution happens to be, okay, if you go to your math course, check it out. Theta dash is a by eta sine of lambda eta plus b by eta cos of lambda eta exponential of minus lambda squared tau. Okay, this is the form of the equation that fits that differential equation. Equation 4.2.2-15, and theta is nothing but 1 plus sum over n equals 1 to infinity 2 minus 1 power n eta by n pi sine n pi eta exponential minus n squared pi squared tau. Okay. So this is what it is. So what is eta? If you recall, eta dash of course is 1 minus theta. Sorry, theta dash is of course 1 minus theta. And what is theta itself? We had defined as the temperature variable, right? T minus T naught divided by Ts minus T naught. Okay. So from, if you have a variation of theta, then you can pick out the variation of T just by a quick transformation here. So, but having it in form of theta makes it general, theta versus eta, or theta versus xi, is it? Yeah, theta versus xi for various values of tau. You get, this is theta, this is eta, this is T minus T naught divided by Ts minus T naught, and this is eta r by r, and this is for various values of the non-dimensional time. Okay, at time equals 0.005, this would be the profile of temperature in the droplet. At tau equals 0.01, this would be the profile of temperature, point of theta, that is, which is nothing but temperature variable. At 0.05, it will be like this. At 0.1, it will be like this, and so on and so forth. So as tau increases at some point in time, everything will reach 60 degrees C, which is this value. Okay. Now we need a certain time. We are working out a problem, right? So to have some feel of the times involved, the tau needed for the temperature at the center to say reach 99%. If you want to reach 100%, it's infinite time, the way the problem is set up. Okay, so if the for it to reach 99% of the surface temperature, turns out to be about 0.5. So that is what this one shows, right? Yeah. You go on, you work out the various profiles. For it to reach 99% here, you need a tau of 0.5. Okay. So for steady state condition, tau equals 0.5, approximately steady state condition. So alpha t by r squared, which is tau, is 0.5. So the time that is needed for steady state is nothing but 0.5 r squared by alpha. Okay, just transposing this equation. And for a spherical drop, like the one that we considered here, 10 microliters, the radius you can get from the volume, 3v by 4 by 3 pi r cube is nothing but the volume, and therefore 3v by 4 pi to the power of 1 by r is the radius. You substitute the values, 3 volume 0.01 by 4 pi. Okay, this is one, recall the value there of the volume, that will turn out to be 0.01 in terms of centimeters. We have it in terms of centimeters here. Okay, so 10 microliters, right? Yeah, sorry, not centimeter cube, that is 10 microliters, and therefore that is 0.01 centimeter cubed, and therefore we get 0.134 centimeters as the radius here. 1.34 into 10 power minus 3. Yeah, this is 0.134 centimeters, that is 1.34 into 10 power minus 3 meters. The alpha of water turns out to be 1.5 into 10 power minus 7 meters squared per second. Okay, remember this is thermal diffusivity. Note the units here, meter squared per second. Same as mass diffusivity or kinematic viscosity. Thermal diffusivity here. Nice to remember that value for water, 1.5 into 10 power minus 7 meters squared per second. And therefore, the time that is needed to reach steady state, 0.5 r squared divided by alpha, turns out to be 6 seconds. Quite decent, right? The entire droplet is going to reach 99% of 60 degrees C in about 6 seconds, which is a good design. Okay, you can very quickly, within 6 seconds, it reaches the temperature. So that is the temperature that is needed for the reaction to go to completion for the next step to occur. So that's perfectly fine. Okay, I think we will stop here for this class. We have completed the chapter on thermal flux. It's a short chapter. And we looked only at the heat flux as a function of its primary driving force at temperature gradient. Okay, conduction alone. All the velocities were 0, as you saw. But we needed that formulation for it to be complete, so that which we can use later. So the primary driving force for heat flux is the temperature gradient, and we saw only temperature gradient cases in this chapter. When we meet next, I will briefly review this chapter and then move on to charge flux. See you then.